Diba? And edu. So backgrounder ini ha. Mag-i-English nga yan ako. So backgrounder ito ng Robustness diagram with loop and time controls. So RDLT. RDLT is actually an offshoot diagram to Robustness diagram of the UML. This has been in existence for many years already. You can find its UML 2.5 na version. And at the time, it was conceptualized to bridge yung you have a set of UML diagrams na structural. Say, isang example niyan ay class diagram, no? So structural meaning I would want to capture the components that are found in the system and the roles that they play. Usually, if we talk of structural models, it doesn't really capture the sequencing of tasks, no? And if we want to know, say, the processes inside that, you have to build another set of diagrams belonging to behavioral diagram. So one of those is the sequence diagram, no? So sometimes you would have to counter check from class diagram to sequence diagram or vice versa, so that you'd be able to realize and capture the entirety of the system. So there is, for a number of years, there was a gap in trying to bridge how we interpret and design the different profiles of a system by counter-checking, cross-checking every now and then all of these diagrams for whatever diagram you have created, no? So the Robustness diagram actually bridged the gap from crossing structural towards the behavioral models and back, because Robustness diagrams would have components there that can help you cross that bridge, no? So the RDLT was conceptualized to extend its power, no? So now that it would have resets, for example, no? Resets wherein you're capable of providing a representation of some components that would perform resets and group them according to some configuration there. And what else? Some of the arc attributes and vertex attributes were added. Previously, it's not really defined or formalized in Robustness diagram. So the three types of vertices, these were already defined in RD, but then we extended it to have a vertex attribute called M. So the three types would be entity objects, boundary objects, controllers. Now, if you want to represent the components of a system which would talk to the environment, or group subgraph inside your system representation, and then abstract that, and then all the information here would be local only to this subgraph, no? So you can introduce the setting 1 to the vertex attribute of this boundary object, and therefore this becomes the subgraph known as the reset bound subsystem. And then it will talk outside. This is still the RDLT, but since may localization na tayo dito, so ito yung nag-act bilang interface node, no? Towards whoever would talk to this subgraph. Okay, so this can also be a boundary object, and then there is some floating dito na interaction, no? Na maybe coming from another RDLT to model the environment interaction. So, ayan. So that's a boundary object. Entity objects are used to represent components of a system that are internal to it. And then controllers would be representative of the tasks that a component or the system itself would execute at some point in time. And they are connected via arcs. So the general rule, and this is even a rule before in the robustness diagram, that you can only connect two vertices if one is an object and the other is a controller, or vice versa, controller to object, or they are both controllers. It should not be the case that two objects will be connected directly to each other. Okay, so that's a rule in constructing arcs. Now, in RDLTs, and this is not found in RD's robustness diagram, so the arc attributes are labeled with itong annotations na to. Okay. If the annotation here, so yung annotation, dalawang values actually to. This represents the constraints, and this represents the maximum number of allowable traversals. Okay. So we have names for it later. Now, so if this is epsilon and this is a label or an attribute value of the arc that is connecting an object towards a controller, this means that this object owns this controller. That means ideally you should be able to access this method through the activation or through the use of this. So yeah. And that is also how we would induce this robustness, this reset bound subsystem, the RBS. So we look up the set of controllers which are owned by this object, which is marked with its M attribute equal to 1. No? So, and group that. So W1 is owned by W0, W2 is owned by W0, nothing else. No? So this ownership, that means whichever controllers are owned by this. So this forms the entire RBS, including this owner. No? So we call this actually as a center of the RBS. And the rule is, if you want to best practice, no? If you want to interact with the RBS, it's good that you first interact with the center. No? Enter that, and then when you leave the RBS, everything that you store here as a dynamic value will be lost. It will be reset. No? So later I will show how are those values formed and how are the resets are done. Okay, so let's go to the details of the arc attributes. Okay, so we have two arc attributes, the C attribute and the L attribute. So first, okay, so for the C attribute, we can have epsilon, okay, or we can have a condition which belongs to a set of conditions sigma. So for epsilon, it can mean ownership, or it can mean simply that there are no conditions imposed when we do a traversal. But if the condition you put here belongs to this alphabet, this means you need to satisfy the constraint. So if there are multiple incoming arcs, no, say this one, multiple incoming arcs come from X1, come from X3, and they are differently set in terms of constraints. And therefore, if you want to reach X5, you need to satisfy B and D. Okay? And if these are present and you have not satisfied this prior, you can never also traverse this. No? You need to satisfy this the first time and reach X5. And then if you look back, and then for example, eventually the path goes back to x2, this can already be traversed. No? So, yeah. Okay.
So what happens pa if yung like kailangan talaga
mag-backtrack. Kung sakali na dito ka nauna, okay, this was from x2, you reached x2, and then you try to check, no, if I can traverse towards x5. If this has not been traversed before, this can never be traversed. No, so the algorithm should backtrack and try to find paths for which it will lead to x3, and then a check will be done here. And then of course this cannot be traversed immediately. You have to find this and satisfy this. No? Okay, that's just one of the conditions. No? We still have to consider this L attribute, the maximum number of traversals allowed. So yeah. Okay, so the that's the epsilon C attribute value, or the condition in sigma. Okay. And we have the L attribute. So this represents the maximum number of times an arc can be traversed. So you can never again use the arc for checking or for traversal if this has been exhausted. And we can verify if the arc traversals already reached this maximum through the use of the T attribute of the arc. So this is the time of traversals that will mark, okay, when did I perform a check or when did I perform a traversal? There are two operations before you can even traverse. No? Okay. Check would just evaluate if the maximum number of traversals still allow you to traverse. And then the subsequent evaluation will be, okay, if my L allows it, then are my conditions satisfied? Yeah. So yeah. Okay, so this is the L and the T. So yeah. Now, if we have defined an RBS by realizing, okay, which object vertices are marked with their M attribute values equal to 1. Therefore, we can have an RBS induced by this center as well as the owned, no? And the arcs that would connect them. So that's the RBS. So the definition of an RBS now implicitly induces typing of arcs, meaning there are types of arcs. No? If we evaluate if we can reach this target node. So we have bridges towards or outwards of the RBS. So an arc is a bridge if it would connect one component outside of the RBS towards inside, or vice versa, from the RBS towards the out. This would be an in bridge of W0, and this will be an out bridge of W2 Y0. Okay, now what would be the impact of types? The types, no? We say that these two are type alike if they are bridges to node it connects to or emanates from, no? Or they're not bridges at all. So for example, x1 to x5, x2 to x5, they're not bridges at all of x5. So they are type alike. So type alikeness you check for asking if the target will be reachable. Okay, so for example, for this two, they are type alike. You check them with each other because they are type alike in realizing if W0 will be reachable. But you don't check W2 to W0 because they are not type alike if you come from the outside, no? So just like in programming, you only consider if you would want to enter here, if the parameters coming from the outside are satisfied, no? Upon entering, that's a time that you can consider here, no? But you've already reached this. So for example, if there is another incoming arc to say from W2 to W0, and that is labeled differently as G, so that means that arc plus this arc you are type alike because they're not bridges to W0. So you need to check the two if they are satisfied. So yeah. So yeah, that's type alikeness. Are there any questions? So so my question would be, is X5 to W0 and W2 to W0 type alike?
No.
No. Is X5 to W0, W0 to W1 type alike? No. Is saan pa ba? W1 to W2, W2 to Y0 type alike?
No.
No. If there is an outbridge from W2 to Y1, are they type alike with respect to W2? Yes. Okay, so that's type alikeness. Okay, so that's a reference point if you would want to evaluate if the target, their target, would be reachable. Okay. So for example, okay, if we would want to extract the purpose of by the way, the purpose of all those arcs and vertex attributes would be to mark which components interact with each other in executing an activity. And most especially, we use the T attribute, this one in red, to mark, okay, have I checked this already? Did I traverse this already? I would mark it with the time of check or the time of traversal of that arc. So, yeah. I think the next one would be simulation. No? So, let's see. Okay. So suppose this is the configuration at times step. What's the value here? 3. No? Suppose I have reached x2 at time step 3. Okay. You'll be able to check that because that will be the most recent will be the maximum of time marked in the T attribute towards x2, no? So 3 at time step 3, we were able to satisfy B and A and reach x2. And now we would illustrate how do we do the checks, how do we do the traversal, the actual traversal. Okay, so from a reference vertex, if there are multiple arcs from that vertex towards some other vertex, so you non-deterministically choose which one to consider. Okay, so for example, here x2, there's no other arc, so we have to choose this, no? Okay, so the check would be to ask, okay, have I done or have I exceeded L here, the L attribute? So at this point in time, this is supposed to be 0, no, initially. But at this moment in time, we have not reached the maximum. No, we will not exceed the maximum. So the number of zeros here would correspond to what is L. No, kasi this will mark, okay, the first time this is checked or traversed, it will be placed in the first element. The next time that you also consider this, it will be put in the second element, and so on. So yeah. So this is the first time we have considered this. And the check operation would mark this first element by using the maximum value of the incoming arcs of x2. So what was the most recent time of reaching x2? And then plus 1. Kaya siya ganyan, 4. So in-underline ko lang yung check time And then yung pag hindi ko na underline kagaya nito, that would be marking the time of traversal. So the check does not really traverse it immediately. We just evaluate this regardless of all other things, no? And the reference would just simply be L. Do I exceed L now? So that's the check operation. So this is 4. And then from the check operation, the second evaluation be, is it unconstrained? No? Unconstrained meaning, okay, we now consider the C attributes, no? And ayan. Ito yung unconstrainedness criteria. Tatlo yan. There are 3 conditions that you need to check for type alike arcs going towards Y2. No? So type unconstrained ito, and you can traverse if it's unconstrained. If all other type alike arcs of X2 and Y1 would have epsilon, or it would be all C, no? So that means no conditions imposed other than itself, C, or we have the same conditions. So that means if I have the same set of conditions, I would be representative of all those other conditions. And therefore, there's no need to satisfy the other conditions, and then I traverse that one. So that's the first condition. If that is true, this will be unconstrained, and therefore you can traverse this. The next one, okay, itong dalawang to would be for cases wherein there is at least one type alike arc which would be differently valued. Okay, so the case should be, okay, all other type alike arcs that would have different C values, C attribute values should have been checked prior, and maybe backtrack, no, was done to find this, no. So all other differently set C values should have been checked. And if they are, of course, this will be unconstrained. So the last C value, which is different from the others, have been checked, and therefore everything is already satisfied. So you can traverse it, no? Yeah. And the third one would be the case that I talked to you before. If I am epsilon, and then there's sigma, no, the conditions A, B, C in the other, but all of them had been considered or traversed before. So this is unconstrained. So for this, for example, at time step 4, this is C, and knowing that there has not been a check operation or check operation that has been done kasi 0, 0 pa to. This means I have violated this, no, the second one, and therefore I would need the algorithm that extracts the activity would need to backtrack to X and then find another path. If there's none, go to the parent and then do a non-deterministic choice again to perform the check, and then checking for unconstrainedness, and then proceed until you can realize that, or the algorithm realizes that, oh, I'm already here, and then I'm able to check this. Yeah. Okay. Clear? Clear naman na. So now, ayan, this is unconstrained. This is no, it's not. It's constrained because of this, no? So suppose we have reached X1, and the value, say the time of traversal here was 2, no? Upon backtracking, kabalik ka, and then you reach this. So same pa rin. So check operation, does this allow? L allows traversal, yes. So put the maximum +1 here, so 3, and then check for unconstrainedness. At this time, this already is unconstrained, no? So there's no other sigma condition that's not yet been checked, and therefore you can traverse this, and that would mean all other checked values for all the other arcs incoming to Y would be traversed and marked at that point in time. Now, what would be the value that I will set here for all the check values? Ano yung gagamitin ko to update that, okay, I was able to traverse this.
Yung T.
But we have the check value here 3 and we have the check value here 4. So would I use 3 or 4 in realizing that I've reached Y2? It would be the
Yung
maximum.
maximum.
Because that means, okay, the longest path to which the last would sigma condition was satisfied. Or kung epsilon naman, edi yung epsilon. This means this would take the longest amount of time. So at that time, times step 4, I was able to verify na okay, this is all unconstrained. Okay. So we traverse all of these checked arcs and then update. Yan. So lahat yan ng mga type alike na na-check na, ma-update din. Okay, so kung na-check din to kanina, yan, update din yan. Okay. So all of them will be 4. Okay. So from Y2, just proceed, no? Again, non-deterministic choice of outgoing arcs, and then do a check operation, and then verify if it's unconstrained, and so on and so forth. No? So S1 would be the list of arcs traversed at the first time step, okay? And then you proceed until you find the target sync vertex, no? Okay. Now, what would be the implication of having a reset bound subsystem? Now, say you do again the activity extraction. Okay, for this case, this is a check. Is this unconstrained? You have E and E. So pareho lang, unconstrained, and then so you can actually access immediately, no? So 4 and 5, and then you traverse using the same strategy, no? And suppose that, okay, by the way, yan, kagaya ng kanina, ito, 7, no? 7. You don't need to check this because once you do a check here, this is not type alike. So you can just proceed immediately, no? Even if this is G and this is E or E, no? So they're not type alike, you can immediately traverse this. Okay, so so we just simulated the activity extraction here until we reach W2, and then the algorithm chose this, no? Okay, so the maximum, the last one would be 8, no? And when we traverse an out bridge, okay, what would happen? So the check would be 9, check time is 9, and this is unconstrained. And then once you traverse this, okay, everything is reset. So anong mangyayari? The T values here would be reset. Okay, the arcs that you have traversed before were already marked, no, by the S sub I. They're already marked. They're already permanently there. But the T values are reset to 0. So what's the implication there? That means if this one is 1, and previously had I marked this as 1, the check operation would forbid me to consider this again, right? But because I reset, it's as good as I never used this, no? So you can actually loop back, and then it's as good as this has never been used, no? So yeah.
So niabali po ng maximum na pag-traverse ng arc kay kung localized lahat time na nasulod niya.
Ito, L din, kung ito din naman, hindi naman to RBS. So there's no reset that will be done. So for sure, hindi naman siya na-reset. So kung nagawa mo na to, ito, isang beses, hindi mo na talaga siya magagamit ever. no? So that's the power of having volatile structures. If it will be a huge system and this is a shared resource, o di ba, pwede mo siyang magamit po ng paulit-ulit. Yan. Okay, so for this simulation of the activity extraction algorithm, the generated activity profile is this S1. So usually may siniset tayo na kung saan nagsisimula. So for this case, sa X0 tayo and then nag-traverse siya sa X1. Siguro nag-backtrack yan kaya nag-consider siya papunta din dito. So papunta din dito. So X1, X2. So this models yung parallelized na pag-execute, no? Kasi time step 1, no? So, yan din naman ang kagandahan. Namo-model mo talaga na hindi to parang other values kasi na-consider ko na yung andito sa ano, di ba? So, we always reference ano yung maximum papasok sa kanya. Kung source naman, wala naman. So, siya talaga yung una. So, this would be 0 plus 1. So we can mark parallelism sa activity profile. We can mark if they're differently set conditions, we know they are simultaneously satisfied, no? Say si X3 and X5 and X1 and X5. Yan. So reflective siya ng which set of conditions are to be satisfied. And you can enumerate as many of the components, the art components of an RBS for as long as they're still usable, no? So the limit to entering the RBS would be constrained to the allowed traversals here, the L2 of its in bridges. Ayan. So for this case, ano yung maximum kaya na number of entry that can be done here?
3.
3. Yes. I get. Yeah. So, you actually input to the activity extraction algorithm the final, your target, no? And once that is reached by traversal, so the algorithm terminates. And so at S of 9, time step 9, yan. Hindi pala, mahaba pala siya. So ang katapusan pala dito is, yan, trinaverse niya yung Y2, yan, nandito na siya, at time step 19. Okay. A bad design practice would be to set looping arcs with conditions, no, in sigma. Because what would happen if this had been sigma?
I-check pa yung condition.
And you cannot proceed, no? Kung sakali. So you have to be careful in designing RDLTs. No? Yeah. So that's the end. Yay! Are there any questions?
If ma-terminate na po, yung magre-reset ba lahat ng T attributes?
For the next simulation, you can reset it. Yeah, usually dapat nire-reset mo yung kabuuan because you would be simulating another case or another activity. No. Yeah.
So ano po ngayon usually ang magiging conditions of sigma?
You can use whatever condition that would apply to your system. So for example, this is abstract at the moment, no? But when I apply this to a chiller system, you would be looking at temperature values here. So this represents a logical expression. I say if T is greater than this temperature, you can have any type of condition that would be there for your system.
Answerable by true or false.
True or false. Yeah. For gyros, and I've had a student advisee that represented this condition as a parameter value pass, no? Say send M. So rather than a condition, I say it's like a parameter constraint. I'm expecting a value M to be sent from the source node to the target. Yeah. So you're free to represent any condition. If you're dealing with real world conditions. Yeah. And if you are also dealing with resource allocation, diba? In the real world, you can limit the resource allocation by setting L. Yeah. Okay, so yeah. Are there any questions?
Anong meaning mo hindi nga kaya ano sa gihapon na iba nga number?
This is the second time of traversal.
Ah,
Oh, you don't overwrite the value once it's already traversed. Now that marks, okay, this is the first time this was traversed or checked. Na-underline ko lang yung check. At the time na traverse mo na siya, ina-update ko yun. And then wala na siyang underline. So, naka-set na siya na ganyan. And that will be the time here, S sub I. So, time step is 9. No? Okay. I traverse W2 to Y0. So, kaya alam mo, pag nag-reach ka na ng maximum na allowable traversals, kasi those would correspond to the number of positive values in your T attribute. Kaya yan, ito. Yan, 0 ulit. Hanggang sa una talaga.
so pwede po ngayon ma'am, anti-attribute kay aniya timestamp and pag-traverse.
So it reflects the dynamic behavior of the system as you execute an activity.
So baga po yan, sequencing talaga.
Yeah. So we'll talk about yung problem na ma-inherit mo sana from
From
kung wala ka ng question dito sa intro, I can stop muna.